Thank you for coming, and thank you to the organizers for inviting me here to RubyConf India to speak at this event. So that's the title of my talk today, and looking for the crowd, I guess sex do sell. Right? And I'm being very honest about it. I think that's one of the big reasons why I put that. So the actual thing that I'm going to talk about is simulation and data analysis with Ruby and R. But I suppose if I use that as a main title, maybe like a fifth of you would turn up. Okay, so let me start off by telling you where I come from. I come from this island called Singapore. That's a small little red dot at the end of a peninsula, the peninsula Malaysia. And I did a little bit of research last night after coming back from the drinks at the speaker session, speaker dinner. Singapore is about 700 square kilometers, and I just found out that Pune is also about 700 square kilometers. So yeah, and Singapore has about 5 million people. Pune, I think, from Wikipedia at least, it has about 3.6 million people. So anyway, that's where I come from. At this point in time, because I was born in Malaysia, but I've been living in Singapore for the past 20 years. So about me and what I do, right? So I work for a company called Hewlett-Packard in Singapore. I suppose most of you know what HP is. There's a lot of news recently. Most of it not too good, but HP is still a great company to work for, and I'm very proud to work for HP. I work for a part of HP, which is called the HP Labs. And the reason why this picture is in black and white, and we have some old guys in there, because HP Labs is quite an established and old organization that does research on behalf of HP. We do scientific research as opposed to developing products that will be sold in HP eventually. We develop advanced technologies that hopefully one day will be transformed into HP products. So that's my job. But exactly what do? I go one level lower. So we do cloud computing. So my lab is primarily focused on cloud computing. So why am I talking about Ruby here in India when my job is about cloud computing? That's because of Ruby is my passion, right? So Ruby is a passion for me, has been a passion for me for the past 6-7 years. I've been doing Ruby for reasonable amount of time. I've done Java much longer. I've done Java for 11 years. And I was speaking to some of my friends that I met here in India yesterday, that I did Java for 11 years. And one day I just woke up and I said, no more. That's it. And I stopped because that was it for me. But very soon after that, I discovered Ruby, right? And that sort of brought my interest back again into programming. And I've been programming non-stop since then, right? And I've been enjoying every single day of it since then. Okay, but besides Ruby, I have other loves, okay, which is R. So R is the other language that I'm interested in among the other languages. So basically what Ruby brought back to me is not just the interest in programming, but also the interest in exploring different other technologies beyond Java, which I was doing for the past 11 years. I did everything in Java, but it was only in Java, right? But after that, I began to open up my eyes a lot more wider to the other technologies and other environments, and I learned a lot more since then. Okay, so let me jump straight into the talk that I want to do today. Okay, it's not coming up, but I'm getting some things. Yeah. Any idea what this is? Does anyone know what this is? Pelicans? No. Fish? Birds? Tortoise? No. Okay, so it's actually this bird, right? It's a very common bird. It's called a common starling. European starling, obviously, I think it's originated in Europe. But here in India and also in Singapore and Malaysia, where I came from, It's very related to a bird called myna. So it's actually a very close relative of the myna. And some of the behavior that you notice in the mynas also reflect here with the common starling. And one of the most spectacular things about the common starling is it's basically this, right? They tend to flock. They tend to gather in huge numbers. So there was a research that talked about them flocking in about 1.5 million, right? 1.5 million birds within a single flock. That seems pretty terrifying, but yet at the same time very beautiful, right? Because they all move together at the same time as if it's a single animal. And if you've seen one of these guys, besides thinking of the Alfred Hitchcock movie Birds, you will also think of, wow, I mean, what is really happening here? But flocking. So what I want to talk about today is related to birds flocking. And what I'll be doing is I'll be taking a base simulation, and then I'll be transforming it over the next few slides and talking about how we can use this base simulation to discover more about the world around us. And before I do that, I want to talk a little bit more about this base simulation. Anyone know about Boyds by Craig Reynolds? Maybe a quick show of hand. No? I thought I heard somebody mentioning Boyds earlier on. But anyway, Boyds is this research done by this researcher. His name is Craig Reynolds, and I think he did it in 1980s, so it's been some time ago. Basically what it does is it models animal movements. What kind of animals? So animals like birds, like fish, any kind of animals that move together in the same way, flocking or schooling or whatever kind of related movements. So basically what he did was he used three simple rules. And these three simple rules, when the individual Boyds in it follow these three simple rules, it resulted in flocking, right? And the reason why it does that is because it's emergence. It's emergent behavior, complex behavior arising from simple rules, right? And eventually, this became the basis of some of the more spectacular special effects that you see. If any one of you have seen Lord of the Rings, and I'm quite sure everybody has in this room, you notice you remember the scenes where the orcs were fighting against the elves, right? And they all seem to moving individually, autonomously. In fact, they are, because it was simulated, and the elves and the orcs were actually fighting as autonomous agents within that film, right? So very, very interesting technologies. So what are the simple rules that I was talking about? So three basic rules. First is separation. They move to avoid crowding on the flock. So they don't want to move together. They want to crowd each other, right? Second one is alignment. They always try to move in the same direction. And third is cohesion. They want to move together in a flock, right? So just three simple rules. And it results in very, very lifelike actions of birds flocking or fish schooling. And using that base simulation, what I'll be doing in the next few slides is go through something called agent-based modeling, also called multi-agent simulation. Basically, it's about autonomous agents, in this case, the Boyds, interacting with each other and as well as the environment. And we use this simulation to analyze different things, right? And the three things that I'll be talking about today is the things that I'll be going through later on. But agent-based modeling has been used in things like supply chain optimization, traffic pattern optimization, economic models, and about the spread of epidemics and so on. Any one of you probably have gone through com science, have heard about the John Conway's Game of Life? Yes? Yeah? It's great. I mean, it's com science is. So this is very much similar to that, except it's on a different level. Okay? And the project I've been doing here, the research I did here, it's heavily influenced by Epstein and Extel's Sugarscape. Have anyone heard of Sugarscape here? No, but there's excellent research done by these two researchers, and I'm just writing on top of them. Right. Of course, I do it in quite a different way, but the basic ideas actually come from these two researchers. Okay, so let me get into my simulation. It's an artificial world, which I call Utopia, and it's populated by roids, obviously Ruby roids. Okay, And these roids are free to wander through an infinite landscape. So we just move around in the landscape. Okay. All the simulations I've done here are using Ruby, and I use shoes. Okay. So let me just show you the simulation. Okay, so these are the roids moving around, and they will just move around, right, following these three rules. And as any time they move from one edge of the screen, it will come back from the other. Now, if I put a kind of obstacle around it, what happened? It will just move around the obstacle. And I did not program how they move around the obstacle, right? They just follow the same three rules as they move around. So that's the base simulation. I'll get on into the kind of analysis I'll be doing next. The first one is about money. So, anyone heard of the Occupy movement? No? So I think almost everybody has heard about Occupy movement, which is a international protest that sort of protests against the economic inequality between the haves and have-nots, right? Basically, it's about that a small minority of people having a larger share of the economic pie, right, that's in existence. That 1% should not live on the expense of the 99% of people. So we know of this phenomenon, which is not a new phenomenon, but why does it happen? And how does it happen? Is it a natural phenomenon? Is it something that's caused by human beings, certain human beings, certain fat cats who would greedily hoard everything? So this is the first analysis I'll be doing. But before going to analysis, I need to change the behavior of the base simulation. So first of all now, previously the roids will just happily move around the screen. But now I give them an energy level. So each roid is randomly assigned an energy level. And at every tick, at every count, they lose one energy. When the energy reaches 0, it will die. Okay? So if the roid do not want to die, it will need to seek out food. It need to seek out food and consume food. Consuming food will replenish its energy, and it will continue living, right? So as long as it has food, it will not die. Basically, it's immortal. So this is the first simulation. You notice here the green stuff, that's the food. It's randomly generated and populated on the screen. And you notice the roids running around, scurrying around looking for food, consuming it and getting larger in effect. You see the roids actually shrinking. They're actually losing energy. And when they lose all the energy, they will die and disappear off the screen. Okay, so that's the first simulation. And how do I do an analysis here? So every tick, I record the energy level of every roid. And I'll do this until the end of the world, basically, the end of the simulation. I count down from 2000, and I do a tick by tick until it reaches 0, and then that's the end of the world, right? After that, I do an energy level analysis. Okay, so that's t equals 1, and that's t equals 500. I did not put the t equals like 2000 because after 500, the patterns are about the same. Anyone here can tell me what you can observe from this energy level analysis? The food has? Food has finished, exhausted. Some of the food is slowly decreasing as respect to time. Yes. The energy level has decreased with respect to time. Anything else? Sorry? Okay. Okay. Good observation. It gets tired and then it gets tired. Or gets tired weak. Yes, of course.
Maybe the energy. Hello. Maybe the energy level is higher towards the center of the graph. Energy levels are at the peak towards the center of the graph, and then they slowly decline.
Yes, they slowly decrease. The very first one, t equals 1. you notice the distribution basically is normal distribution because uh, I randomly assign a energy level to all the rods. Right? Sorry, you saw insist. Yes, very good observation. Yes. Yes, you're right. You're right. So let me move on to the next slide. Um, Basically, that's the slide that talks about t equals 2000, right? At t equals 2000 on the day of reckoning, what happens is that most roids are dead, like zero energy level. But you have a few roids that have a lot of energy, right? So and I started off, I randomly assigned 0 to 100 energy level, right? That's why you get this nice random distribution. But at t equals 2000, you got some roids who have like 1004, 1006, right? So they have massively more energy level than any of the roids. And in fact, they could live on for a long, long time, right? But most of the other roids are dead. Okay. So basically, it shows a kind of distribution that is not normal at the end of the day. And of course, you can notice that it's not equal. But let's get to something that's more precise. How unequal, right? So the Gini coefficient. Any one of you know what the Gini coefficient is? It's something that's used by economists, but basically it's a measure of inequality, right? Where 0 is perfect equality, everybody is the same, and 1 is perfect inequality, where one guy has everything and everybody else has nothing, right? So the Gini coefficient is a number that is between 0 and 1 that depicts the amount of inequality in the system. Okay, and the Lorenz curve basically is the graphical way of depicting that. Right? So the curve, that curve between A and B, that depicts the inequality. If it's 45-degree angle, it means perfect equality, and if it's a horizontal line, it's perfect inequality. Right. So let's look at exactly the same data, but using the Lorenz curve. And you notice when t equals 1, because it's random distribution, it's almost entirely equal, right? T equals 500, there's a lot of inequality. And that's the observation I think most of you get. Over a period of time, a small percentage of the population gets a large percentage of the energy. So what do you think is the cause of this? Any guesses? Greed. Okay. Sorry? Okay. Okay. Proximity to food resources. Okay. Okay. Right place at the right time. Okay. Survival of the fittest. Okay. I'm coming to that later. Resources. They have more energy, to got more energy. Good. Okay, so let me throw a bit of a spanner into some of these answers. So all the roids are the same. I didn't give any special powers to any of the roids, right? So there are no specifically greedy roids or particularly powerful roids that have special powers because they are all randomly generated with random amounts of energy. So you notice the random distribution at the beginning. And of course, if somebody mentioned that if it's lucky, then some of the roids are luckier than the others, then of course the end should also follow a random distribution. But in fact, it doesn't. Like, it follows some kind of power law. So any more guesses? Okay. Not giving the others a chance. Okay.
Conservation of energy. Conservation of energy.
Conservation of energy.
Yeah.
Okay. So they all are exactly the same. So it doesn't really matter how well
the energy is actually distributed to a central source. It's not distributed evenly. That is the problem. If it's distributed evenly, people can the bots could reach it easier.
So the amount of food is actually created randomly and distributed randomly on the page. So basically everything is random. Yes. The conservation of the growth is not being divided. Of course, yes.
So yeah, it's essentially greed. Even if you have food, you consume more food as soon as you find something. So you should, if you leave maybe for others to find, and maybe because you have some reserve,
Okay,
you might be able to wait and give someone else a chance.
okay, that's a good observation. Yes. Mhm. Yes, so very good question. I actually did not do that analysis. I actually gave this talk in a couple of times before, and this question came out as well. I did not actually go back and do an analysis of this, so I do not know. But basically, the code is open source. You can actually take my code and do a run on it later.
Follow-up question on that.
Yes.
Is there any competitive advantage that a droid with energy has over one which doesn't?
I think this probably the same answer I will give. I don't know because I did not do that analysis. But again, the code is open source, so you can actually take the code and do something with it and do your own analysis on it.
In spite of energy distributed and consumed randomly,
Yes.
there's a sort of pattern of consumption and concentration of energy at a singular point. Is that what you?
Okay. I don't have an absolute answer.
Okay.
What I'm trying to show you is the simulation and the end result of the simulation. Right. So I'm just trying to, if you give a absolutely wrong thing, you will say something absolutely wrong, I'll tell you. But I think a lot of the answers are actually not wrong. Yes.
Yeah. So I think the droids which start with more amount of energy are more likely to get food during their lifetime and have access to more food. As they collect more food, they're again more likely to collect more food. So and
Yes.
the droids with less energy are more likely to less likely to hit food and eventually die out. So that's why this
Okay.
inequality.
Okay. That's a good answer. Yes. Yes, sir.
Because of flocking behavior, they
Mhm.
flock because they go for the same food. They have a lesser chance of getting the food. The people who are like outside the flock, they
That's-
happen to be in a place where
Okay. Okay, that's a very good observation. I actually do not know the answer to that because I did not say analyze where they actually are when they get the food. Yes, everyone is supposed to. Yes, that's right. Okay, so a bit of proviso. They can only follow the flock if they can see the flock, because sometimes they fall off towards the edges, and therefore if they cannot see it, then they might wander off a bit. But eventually, if they actually see the flock again, they will move back into it. So, it's a random event. That's right. That's right. It could happen. It could happen. Yep. So maybe I should continue before. Yeah, because I think we need to finish by 12. But thank you for your enthusiasm. I think I'm getting a lot of good replies here. So the basically what happened is the phenomenon that you saw is that the rich gets richer and the poor gets poorer. Right? Exactly like some of you have actually mentioned. And it's back to where we started. Emergent behavior, where small changes initially, where say the roids actually get more food initially, they have larger effects over the period of time, right? So the small advantages they get initially actually ripple down to very large advantages at later point in time, and they get a lot more energy then. What it boils down to is basically about simple local rules bringing very complex global changes at a later point in time. Okay, so that's the first one. So the second one is it's about sex, and I think that's the reason why you guys are here. No, I'm just kidding. So the second simulation, I want to make some changes now. So I have the roids to have gender, right? So there are the male roids now and the female roids. Males are blue and the females are gray. Okay. You will see that in a while. So if the female is within a childbearing age, which I define here with 20 to 50 ticks, and if it has enough energy, it will look for a nearby male. And when it finds that nearby male, and that nearby male is also within childbearing age, and has enough energy, then they will procreate, and instantly create a baby roid. Right? So it's instantaneous. Both male and female, after procreation, they will lose energy. Okay, so that's one of the changes that I make. And the second change is with birth, there comes death. Right? Previously, the roids are immortal; they will never die as long as they have energy. But now, every roid is assigned randomly assigned a lifespan, so a number of ticks that they can live. Right? And every tick, I would increase their age. When the age reaches the lifespan, they will die, regardless of how much energy they have. Right? So that's the new simulation. And this is what you see on the screen. So the blue are the males and the gray are the females. You don't quite see it, but because it's very fast actually. But at certain instances, when the blue and the gray comes together, and you see suddenly there's a lot more roids around it, it's because they procreate instantaneous birth. And here you notice that the information I get, the total amount of population, the males and the females. And I'll talk about it in a while. Okay, so the data I collected here, what I want to do now is to investigate how population changes as we introduce sex and death. And at every tick, we collect the population of the entire world, as well as the male and the female. Okay? With what you saw just now in the simulation, how do you think the graph would look like? Any guesses? Okay. And any other guesses? Children will die off. I mean, as they grow old, they randomly assign a lifespan again, and they also age. After a while, they also die off. Yeah. So this is the chart you get, right? And you get a population fluctuation, right? So the males and the females will go up and down, up and down. So the initial down is because the initial population basically ages and then they will die, right? And then as the population increases, and they go up, and then they go down, and they go up, and they go down. Anyone can guess why it goes up and down? Losing energy when they produce children. Okay. Any other? Mm-hmm. Okay, that's a good one as well. Mm-hmm. Yes. Okay, that's a good answer. Any other one more answer? Okay, because of the childbearing age. Okay, so yeah, so basically the reason why it actually fluctuates is because it runs out of food, right? Because there are a lot more roids and because they give birth, and a lot more roids, and the roids consume a lot more food, but the amount of food I randomly generate remain the same. Okay, so they run out of food much faster. As they run out of food, then it decreases the amount of food, and then no more food, they die off, and then as they die off, there are less roids, and then the amount of food has become more than they can consume, and therefore the population increases again. That's why it goes up and down, up and down. But at certain times, this happens. And basically what I did here is actually to change one parameter within my program. And it goes up and down, up and down, up and down, and then boom, everyone dies. Okay, extinction. Any guesses why this happens? Mm-hmm. Mm-hmm. So the number of children it produces is more than one. It can produce more than one. They can have as many as they want. Sorry. Mm-hmm. That's right. That's why it fluctuates. But the previous simulation that I ran, which is exactly the same, except for one parameter that I changed, did not go into extinction. Basically, it fluctuates until the end of time, right, end of the simulation. Whereas this one, I changed one small parameter, and it actually fluctuates after a while, then boom, extinction. Mhm. Right. Okay. So, but why in the previous simulation it doesn't go into extinction, but this simulation it does? Lifespan of the droid increase? No, that's not true because I did not change anything.
Did you change the factor of decreasing the? I'm sorry. Did you change the factor of decreasing the nutrients that you're providing? Did you decrease that factor? That would have affected the entire population going down because the population is increasing and you decrease the generation of food resource.
Okay, that's a good guess. That's a good guess.
Did you
Okay, that's a very good guess.
order the couples? Did you say that?
No, there's no ordering. It's random. I can't hear you. Did I introduce what? Cannibals? No. So I think one of the most popular questions that turn out is asking me is whether there's predator versus prey, right? So I didn't implement that. I know there's like on top of everybody like kill, but no, it didn't happen.
Did you introduce death?
Hmm? Okay, that's a very good guess. No, I didn't change white rules. Sorry? Hmm? Yes, that's the reason actually the extinction, because I think they ran out of females and then only males remained and all died. But it's random. So actually that's not really the answer. No. Okay, last question. Hmm? That's potentially a good answer as well. So I think that gentleman here got it correct. That's actually the parameter that I changed, right? That's actually the parameter I changed. And the parameter that I changed is actually very minimal, right? I just changed the childbearing age from 20 to 25, which normally should not actually have too much impact, right? If that guy is stable. So what am I trying to say here? If you look at the graph early on, a lot of things looks very familiar, right? Things like financial crashes, if you actually monitor the stock market, sometimes it's going up, going down, then there will be crashes and so on. Right? Social unrest, there's a lot of crisis. Animal extinctions, what I was trying to simulate here. So the simulation that I did here suggests that it doesn't really take a lot to trigger crisis, right? That cannot be recovered after a while. Right? And things are not really as stable as you would like to think it is sometimes. So if you see that things are very stable at this point in time and you think, look, this is going to last forever, maybe think again. Right? So I'm not saying that this is the case, right? Because after all, this is still a simulation. But this is basically the results of what I found out in the simulation. Okay, so I'll try to do a little bit faster. So the third one, evolution. Okay, previously all the roids have exactly the same attributes. Okay, the difference only in the maximum lifespan and the energy level. But the new simulation, what I've done is to add on 2 new attributes. The first one is metabolism, how well it can convert food that it eats into energy. And the second is vision range, how far it can actually see. Right? How far it can actually is very useful because it can allow it to eat more food. Okay. Allow it to eat more food as well as to allow it to procreate better because it can find more males or you can find more females. Right? And the roid babies inherit these 2 attributes from the parents. Okay, so how do they inherit? I use a very simple algorithm. Okay, so assuming that the father has genotype small m and small v, and the mother has genotype big M and big V, So the possible genotypes are these, and then what I do is I randomly pick one of them. Right? Because this is not reality, but this is the simplest rules that I can do without coming into a big mess. After all, this is a simulation. And this is the simulation I get. Right? Notice it actually runs a lot slower than the previous simulations. That's because I'm adding a lot more rules to it now. And the thing that I'm mapping now is the metabolism rate as well as the vision range. Okay. And how I collected the data. What I did was at every tick, I calculate the average metabolism of all the roids. And then I map it out in the chart. Now, how do you think the chart looks like? Maybe just 2 answers. Because that's not the end of it. Actually, what happens is the population goes up and down, like in the previous simulation. Any other guesses? Okay, so basically this is the chart, right? And I think there's no surprises, right? Evolution works. We are here, but some interesting things that we can see. The vision range actually improves, although it improves over time. It's not a straight line, right? So there's a bit of up and down as well. And what do you think happened here? I mean, not the up and down, but generally, what do you think happened here? Natural selection. Yes, yes. That's right. So basically, this is the theory of evolution, evolution through natural selection. The roids with the better attributes, surviving longer, reproduce more, and then they have better attributes. Now, this comes a trick question here, right? You notice this chart here. Up to a certain level, it actually flatlines. Right? Do you think that happens in real life? This is a simulation after all. Do you think this flatline happens? It's kind of scary, right? You think it flatlines. No. So yeah, it doesn't happen in real life. But why don't you think? Why do you think it happened here in my simulation? Environmental constraint, yes. Sorry?
Genotypes you had were limited.
Okay. Okay, and life is really random. Okay, very simplistic. Okay. Okay, so I thank you for your enthusiasm. Does anyone read comics here? What's the most recurrent theme in comics that you can think about? Yeah, so basically it's mutation, right? So in my simulation, I did not include mutation. So you will never exceed the maximum, right? But in real life, there's always mutation, and therefore it would exceed the maximum. Okay. Okay, so next. Any guesses what I'm going to talk about next? Okay, so what I'm going to talk about next is whether it's inheritance a good thing. So obviously it's not good for Luke Skywalker, but generally is inheritance a good thing? Because in our simulation, what happens is when a roid dies, the energy has collected over its lifetime is all gone, right? Gone. But what happens if the energy collects over its lifetime, instead of disappearing into ether, it is just redistributed into its children, right? How would it help its children? Will it help its children? And this is the final simulation that I made. It's exactly the same thing. The only thing is that when it dies, it will distribute. So because I do exactly the same thing, I won't show you the same video. Yeah. What do you think happens? How do you think the chart looks like now? Sorry? Much stronger? More inequality? Okay. But okay. Any lifetime of the roid increases? Okay. So yeah, I know I'm running out of time, so I'm just going to flash this. This is what happens, right? In my simulation, this is what happens. So the lighter, smaller dots is basically the original simulation, and the darker one is the one with inheritance. So from the simulation, Inheritance seems to stunt evolution, right? Eventually, though, they will get there. It's just that it slows down evolution quite a lot. Okay, so why it happens, I think I'll leave it up to you guys to think about it, because I don't have an answer for that. Basically, what I've done is just a simulation. And as a wrap up, what I've done here is a simulation. It's not reality. It's not real life. Okay. There are a lot of answers that come up, whether it reflects certain ways that you believe or certain things happen. I think it warrants a lot more investigation before we say this is the absolute truth. But what I wanted to really say here, and my whole point of this presentation is really that programming, things that we all do, right? This is Ruby conference, so you guys program in Ruby, is that you don't only use, programming doesn't necessarily mean that you write just web applications, you write test cases, you do stuff for the business applications, you make lots of money, and so on and so forth. But programming can also be tools that you use to discover the world around us. And this is basically the message that I want to bring to everyone. Last off, if you are interested in the nuts and bolts of it, so the whole simulation is done using Ruby and Shoes. The analysis, I use R, with ggplot and EQ. If you want to take a look at the code, it's available here. And that's how you can reach me. Thank you.